Okay, everybody, hi. This is the Question Barn Show. I'm Ben Tippett. With me this week, Ken Clark, Dr. Ken Clark, my old friend. Hi, Ken.
Hey, Ben.
How's it going? Ken is phoning us right now from Europe over Skype, so there's a little bit of a delay. This show, unlike regular titanium physicists, we have no editing. So it's a lot more fun, but a lot more slapdash. Anyway, this is the show where we answer people's questions that you write in, TIPHYTER at titaniumphysics.com. There's going to be a link on the website. Okay, so, hey Ken, time for small talk. What's new with you this week?
Well, the big thing is that I'm in Europe. I'm at CERN, actually. So right now there's an IceCube collaboration meeting going on. So all of the IceCubers from around the world are descending on CERN to have our meeting and, talk about what we do and stuff like that.
IceCube is it's the great big particle detector, neutrino detector in Antarctica. It's 1 kilometer cube, and it's huge. And we did a show on it, right?
We did.
Yeah, go look in the archives to hear Ken talk about the show. So that's fantastic. Did you just arrive in CERN?
So I got here this morning, actually. So this morning, Europe time. So I've been here for 12 hours or so.
How many hours in a row have you been awake?
So let me think. Maybe I don't want to do that calculation, actually. It's only probably like about 28 now, something like that.
Okay, so as a result, anything you say, they can't sue us if we get it wrong because, loopiness. Well, that's amazing. Thank you for coming on the show.
Happy to do it.
Yeah. This week in my life, what have I been into? I'm just teaching classes. I'm teaching a third-year electromagnetism class now. That's really fun.
How is that?
Yeah, well, the students are really clever, and so they already know calculus. This is the first time I've ever taught students who already know calculus, and they know multivariable calculus. So it's different than I'm used to. I can't get away with glossing over things, and I have to describe things and to them in great detail. But it's pretty fun. I'm enjoying it.
That's very cool.
What else is new? Almost absolutely nothing in my life is new. Blah. All right. Well, and let's.
Well, wait. I could say that I also started teaching class.
Oh yeah.
Yeah. So I'm doing the same lab I did last year and a second year, essentially data analysis course with Python.
Oh, neat.
That should be interesting.
Data analysis is your class full of people? That's like a that's a place people can get jobs in this day and age.
Oh yeah, it's full of people, lots of people, and I'm trying to teach them Python, and I feel so sorry for them that they have to learn Python so fast and from me.
Yeah, well, I worked for a computer lab at a physics department a long time ago when I was an undergraduate, and the lady who hired me to essentially do HTML, run like an SSH website thingy that would let them build and fill in databases so we could like automatically generate people's like university websites, right?
Right.
So you'd click on some university professor and it would look in the database and automatically generate the website based on your level in the university. So if you had higher access level, that would tell you more details, like what their favorite cats were and stuff.
Sure. So
the lady who hired me went on vacation, and so for a week I was supervised by this other guy who was running the lab, and he was a lot sterner. Like, he didn't know what my limitations as a coder were. So I walk into his office on the first day, and he's like, "So, how's your Python?" And I'm like... Anyway, that's it for small talk this week. Let's talk about a question. We got a fantastic question from a guy named Curtis. Curtis emails us. The subject of this is, how is binding energy converted into mass in protons and neutrons? He goes, "Ben, your show is awesome. It makes a 1-hour commute truly enjoyable." As an aside, Ben speaking here, not the letter writer. If nothing else, it helps you sleep through those hour-long commutes. Anyway, I do have a physics question for you, though. Yeah. Why are 3 quarks so light compared to a nucleon? Right. Okay, so brief primer before we get into this. So Ken's going to help us answer this question. Brief primer. Atoms are made of protons and neutrons, which live in the nucleus. We call those nucleons. and it's made of electrons, and the electrons spin around on the outside. You've seen the Bohr model of the atom, etc. I expect everybody to know what an electron is. And then there are these protons and neutrons on the inside. And they're really, really heavy. They're much heavier than the electron, which is why the electron spins around and the neutrons don't really move at all in the middle, right? Or the protons and neutrons don't move at all. Now,
and the electron is a fundamental particle as well.
Yeah, the electron's a fundamental. So they started exploring this. They're like, well, this can't be it. Let's keep smashing things together to see if these things are made out of anything. And it looks like electrons are fundamental. They're not made of anything else. They're just there. But protons and neutrons are made out of these things called quarks, named after the guy from Star Trek Deep Space Nine.
I'm going to have to stop you there and say no, that is not what they're named after.
Okay. Well, anyway, maybe they're, yeah. Okay.
Finnegan's Wake.
It is. Yeah. They're named after James Joyce, right? Is that it?
His name also isn't Quark, but yes.
No, I mean, like, it was a word in Finnegan's Wake.
That's right.
That's a James Joyce novel, right?
Is it a novel or a poem? I don't know.
Something.
That was a poem.
I know so little about this particular topic. Moral of the story is they came up with this weird nonsense word for these. You can't let physicists name things because they get really silly. Anyway, we'll talk about that maybe on another show. Maybe we'll have just an entire show of people listing off stupid names for things.
That sounds like, yeah.
So you got these protons and neutrons, it turns out, are made up of not pairs, but triples. So three different types of particles. They're not different parts, but there's these things called quarks, smaller particles, and they clump together in groups of three. And depending on which particles make up the three, you get a proton or a neutron, right?
You got it.
Okay. So here's the big mystery. Protons, neutrons, really heavy. Quarks, not so heavy. How light are quarks, Ken? Off the top of your head, you don't need to give a specific number. Just be like 10 times lighter.
They're quite a bit lighter. Yeah. I can't remember off the top of my head.
So much lighter, though, that if you add three of them together, you don't end up with the mass of a proton or neutron.
That is certainly true.
All right. So that's the premise of this question. Why are three quarks so light compared to a nucleon? All right, Ken, what do you think?
So this is actually a much better question than I thought it was when you originally asked it. So the original way I thought the question was phrased is, why are three quarks lighter than a nucleon? Which is a good question, but this guy seems to already know at least some of the answer. And some of the answer is that there's this binding energy. So quarks interact with something, called gluons. And there's those particles take up for a lot of the mass that's not quarks, that makes up the nucleon. I mean, I think it all comes down to what we call mass, basically. When we say what the mass of a particle is, it's not something that you could measure essentially on a scale, right? What we're talking about there is the energy equivalence of the particle, how much energy that particle represents. And so when you do the energy equivalence of a particle, you need to not only account for the physical makeup of the particle, but also the energy which is required to hold those three quarks together in the structure in which they're in.
Yeah, it's that E equals mc squared deal from, that E equals mc squared equation gets posted so often, and everybody's always using them in popular science explanations, and usually when they do, it has nothing to do with what they're talking about. But here, it does, right?
Here it's everything.
Yeah, we mentioned, listeners, you might remember the show we did with Greg Proops where we were talking about the Higgs boson. The idea here is that energy has mass. Now, that doesn't usually mean very much, but if you can trap potential energy in something, it will increase the mass of an object. So if you take a spring, an unsquished spring, and put it on a scale, a really light scale, it'll tell you its mass. And then if you squish it so that it's tight, it's squished together, compressed, and you maybe keep it in that compressed state. Maybe there's a lock you can put on it so it doesn't spring out, right? So that it's compressed. It has potential energy. That spring will be slightly heavier than it was before. So it is this energy equivalence, like Ken said. Literally, they're saying, okay, the gluon has this much energy and the quark has this much energy, and you add it all up and you end up with the mass of the nucleon. But how do you say? Yeah, it's literally this E equals mc squared. The mass of the object is heavier than the mass of its parts because we need to include the binding energy in the overall mass.
Right. Otherwise, these things would shoot apart, right? I mean, they would reform in some other structure.
Yeah. Gluons are really fun. I mean, okay. Yeah, people aren't used to how much I stutter because I usually cut it out, huh? Okay.
I think it's good.
So are gluons the quantized particle? Are they the gauge boson of the strong force?
The strong nuclear force. That's the gluon. Yeah.
Okay, right. So so Ken said they're bound together by gluons, so there are 4 fundamental forces, right?
You got it.
There's gravity, my old friend, which isn't really a force, but whatever. There's electromagnetism. So magnetic forces and electric fields, like static electric fields, are part of the same force. And then there's the weak nuclear force, which causes radioactive decay. We did a show on that. Go look that one up.
Yes, we did.
And then there's the strong nuclear force, which is what holds all of the atoms together, all of the nucleons together in an atom. And it also holds, I guess, all of the gluons together. I mean, all of the quarks together in a nucleon. And okay, so I mentioned stupid names earlier. Gluon, right? It's the thing that glues them together.
Yeah, it's a pretty lame name, some might say.
At least they didn't call it a stick-on or something. Okay,
it works. Yes.
Yeah. So when Ken's saying that it's a particle, what happens is in quantum mechanics, we often when we're trying to describe the forces generated and calculate the amount of force between two particles, when we quantize the field that's sticking them together, you end up describing the attraction of two particles together, or the repulsion, in terms of the exchange of little particles, right? So in electromagnetic theory, things that interact through electromagnetic waves, or the electric field or the magnetic field, will be exchanging photons, which are quantized particles of the electric field. There are similar gauge bosons for the weak field. We might have mentioned them in a previous episode. I mean, there's the Higgs boson. That's the one everybody cares about lately. And then, so these gluons are the quantized particle approximations of the interaction through the strong field. Is there anything else to talk about this? Oh, yeah. There's one really neat thing.
I think we should talk about why why you can't have free single quarks.
Yeah, I was about to bring that up. You do it, Ken. You tell them.
Yes, so quarks always come bound. They come in states of 2 or 3, and this actually ties into gluons too, because if you were to try to separate these quarks, I guess I'm doing motions which you can't see. So you take 2 quarks and you try to separate them. As you pull them apart, the gluon, the energy that's required, the gluon is so strong, the energy that's required to pull them apart, you will eventually reach a point in which it is energetically favorable to create 2 new quarks from that energy, and then you'll be left with 2 quark pairs. It's not, at least so far, we haven't seen free single quarks. We can't rule it out entirely. This is, a scientific endeavor, so there's always some chance that in the future we'll do something. It's hard to see how that would happen, but I don't want to rule anything out. But essentially, this is another case of the mass-energy equivalence, where as you pull these 2 quarks apart, you put so much energy into this gluon that it splits and can become 2 new quarks, which is so cool.
That doesn't happen in other fields, because most fields, gravity, electromagnetic, the weak field, they fall off. They become less powerful the farther apart the 2 objects are.
Right. So,
if you take the sun and the moon as if they're sticking together, you take the Earth and the moon. If you grew to an enormous size, the size of maybe God or Superman, you could push them apart, and then there would be less force between them. Gravity, the force of gravity pulling them together would decrease the farther apart they are. Right. With the strong force, that's not the case. The farther apart 2 things that are talking to each other through the strong force the farther apart they are, the stronger their attraction. It's like it's almost like there's a metal spring between them, where the farther we pull them apart, the stronger it gets. And so the farther you pull it apart, the more potential energy the field gets as we stretch the field. And then eventually the field has so much energy that it could convert that energy into building a pair of quarks. And so it does. And then 2 quarks pop out of the vacuum. And then those 2 quarks move out to their neighboring buddies, and the field decreases. It's pretty crazy. Yeah. Moral of the story is things are lots of fun. All right, that's probably it for enough for today. I think that was pretty fun. What's that?
It's a good moral.
Yeah, good moral of the story, everybody. Okay, so thanks, Ken. That was pretty fun. The deal is, thank you everybody for listening to the show. This is going to be we're trying to make this a weekly show. We're trying to make this a pretty easy show to make and a pretty fun show to listen to. If you'd like us to answer your question, send it on down to TIPHYTER, TIPHYTER at titaniumphysics.com. I will add it to the pile of questions, and then every week I'll have one of my favorite titanium physicists. You're my favorite titanium physicist, Ken. That's why you're on second.
That's so nice of you.
I'll have one of my buds on, and we'll answer your questies, and it will be super fun. Okay, everybody, see you next week. Boop.